All right, it's the infamous Oregon water problem, guys. All right, this is our last big one. It's really good for you to focus on kind of the context, the units, that sort of thing in this problem. So, the rate of consumption of bottled water in Oregon, W of T, is given in the table below, where W is measured in millions of gallons per year. So, I'm going to just throw that on there for my units. W of T, millions of gallons per year. That is fun units. I'm going to enjoy writing that many times, I assume. And T is measured in years from 1980 at T equals 0. So maybe you just want to say like this is 1980. Or maybe you want to do a couple of these. Well, 10 years later, this would be like 1990. And this would then be 1996, I guess. I just give you a little bit better idea of what all of these dates are looking at with our T's. All right, so using the data in the table, determine the average rate of change. Average rate of change. So that's going to be AROC. In the rate of consumption of bottled water for the 10-year period beginning in 1980. Include the units. Yeah, so a couple important things to be aware of here for, what is this, number one? Yeah. Okay, it's saying the 10-year period. So we don't want to go all the way out to 16. Okay, we want to stop it at 10. So if we want to find average rate of change, we want to do W of 10 minus W of 0 divided by 10 minus 0. Once again, guys, you know 10 minus 0 is 10. Okay, you need to write the 10 minus 0. It's your difference quotient to get your points. Okay, so then really just figure out what W of 10 is. That is going to be 18. Minus W of 0 is going to be 4. Divided by 10. Here you don't need to write it again because you have it written once. Which is really going to be 14 over 10, which I believe is 1.4. Okay, let's just go and reread this to make sure I answered the question because I don't think I did. Using that on the table, determine the average rate of change in the rate of consumption of bottled water for the 10-year period, which we did. Include the units. Okay, so here remember our units. W, I already wrote this down, is millions of gallons per year. And wasn't this our time in our denominator, which was years? So millions of gallons per year per year. So millions of gallons per year squared. Okay.
You're doing AROC on a rate.
AROC on a rate.
Woo!
Okay, but just pay attention. If it actually says average rate of change, that is going to be AROC, not FAVE or any of that stuff. Number 2, using the data in the table, approximate W prime of 10, the instantaneous rate of change of WT at T equals 10. Interpret the meaning of W prime of 10 with correct units. Yeah, so 2 here, we want to figure out W prime of 10. Remember, we're not actually finding the exact value of the derivative because we're just given a table. If you had an equation, you could find the exact value, so we're going to have a little squiggly equal thing. So we want to figure out the derivative at 10, and we're going to use the two values closest to 10 to approximate that. So we're essentially doing AROC again, just with some different values. So this is going to be W of 12 minus W of 8 divided by 12 minus 8.
So we've always heard this, it's called straddling your instantaneous rate of change. Because W of 10 is 18, not W prime, right? That's W of 10. So the idea is to find instantaneous rate of change, you're estimating using the average rate of change. And yeah, like 10 is between 0 and 16, but you have to have the two closest. So you want to straddle the ones that are closest to the instant you're talking about in question.
Okay, if we thought about this, it's just giving us data points. We got like 14.5. We're gonna have 18. And then we got 22. Okay, so really what we're doing is just using these two data points to approximate the derivative at 18. Or I guess at 10, not 18, at 10.
Yeah, you're finding like the slope of the secant line, which is going to be close to the tangent line at that point.
So, this is fun. What do we got going on here? Oh, so W of 12 is really going to be 22. W of 8 is going to be 14.5. Divided by, you can leave it 12 minus 8, or you can change it to 4.
This is calculator active. Maybe I'll write that on the board, which gives you 1.875.
Yay, 1.875. So now for the tricky stuff.
Mr. Herding, this is a really good black marker if you want to bust out this black
Well,
marker.
can we get rid of all the garbage ones? I'm sick of the garbage ones. You always hide the good ones. Okay, so we know that W prime, we just did the same exact thing in part 1. So this units is going to be millions of gallons per year squared. Now that's not what we're really asked to do, but I just wanted to talk about those units again there. So we're supposed to interpret whatever W prime 10 is really meaning in this problem. Okay, so we're really talking the derivative of W. So W was the, oh, you stole my paper, I can't read.
W, it's right here. W is the rate of consumption of bottled water in millions of gallons per year.
So the rate of consumption of bottled water. Alright, I always, whenever I'm doing this, I even say in Oregon. You don't really need to say in Oregon, I guess. I'm gonna, because it makes me happy. So that's just what we're talking about. Okay, this was our derivative of that, which is positive, so we would say is increasing at a rate. Okay, that's what you have to have the rate here. The rate of consumption, because that is really what W is. Okay, and then we always say then is increasing at a rate of about 1.875, and make sure you include your units here, even though I already wrote it up there earlier. Millions of gallons per year squared. Okay, now it's not always increasing at that rate, so we need to specify our time. So 10 is really talking about, well, T is talking about the beginning of the year since 1980. So this is going to be at the beginning of 1990.
And they would probably give it to you if it was yours, if you said at time T equals 10.
It's lazy.
That's kind of the lazy way, but I think they would give it to you either way.
I would dock you.
Okay.
Sweet. That's 2 down and a lot to go. Oh, I get my paper back now so I can actually read what I'm doing. Using the data in the table and a left Riemann sum with 4 subintervals, approximate the value of the integral 0 to 8 of W t dt. Integral from 0 to 8 of W t dt. Okay. Explain the meaning in context of the problem using correct units.
Excuse me.
Got the coronavirus. So we only want to go from 0 to 8, and they said 4 subintervals. So what I would definitely do is something like this. It just helps me see kind of what's going on here. I'm going to go back and erase that. That was for number 2. Okay, so we want a left Riemann sum. So remember, this is not going to be the exact value again. We're using basically a table to help approximate. So we're going to use squiggly equal thing. Left Riemann sum. So really our bases are going to be the difference in our times. Okay, and the height is going to be our values of W of t, but we always want the left one because it's the left Riemann sum. So here my base is going to be 3 times my height is 4 for my left value, plus my next base is going to be 2. Okay, my height on this one is going to be 6.
And you guys, this is pretty typical because it's not equal intervals, so you have to do each rectangle base times height separately and add them together.
My next base has a difference of 2 there. I use my lefternmost value at 7.2. And then I got my last one here, which is a base of 1. And I'm going to use my left value of 10. So I'm just going to write 10. Not a bad idea to put 10 times 1. It shows that you are doing kind of an approximation method.
And since I think we have to interpret this one, we're going to go ahead and show it on the calculator, type it in so we can get like a value to approximate a little bit better. So they're looking for a product and a sum when you're doing Riemann sums, whether it's LRAM, RRAM, MRAM, or trapezoids. So are you multiplying and are you adding? You should get 48.4. If we were doing RRAM, you would have done this guy, this guy, this guy, this guy, and left the 4 off. If you're doing LRAM, this guy, this guy, this guy, this guy, leave the 14.5 off. If you were doing MRAM, you would have had to have equal intervals and known the middle values function tall.
I just want to point out I did that in my head. I didn't need your calculator.
Oh, cool.
I got skills.
Mad ones.
Yes. Alright, so I always like to think about my units before trying to figure out what this is even talking about. So remember, W of t here was going to be millions of gallons per year. If we integrate that, our denominator units essentially are going to go up by 1. I'm sorry, we're going to get rid of that. So this is going to be millions of gallons. Okay, so we have 48.4 million gallons. Okay, so interpreting basically in the context of this problem, I would say Oregon consumed, I can't write, about 48.4 million gallons of water. Okay, and then we want to give our time interval we went from 0 to 8, so from 1980 to 1988. It's a great year right there. One of the best ever. Just
Why
saying.
is that, Mr. Herney?
That's the year I was born.
Oh. Huh.
I know.
Weird.
Yes, you are weird. I agree. Alright, number 4. Using the data in the table and the trapezoidal method with 4 subintervals, approximate the average rate for consumption of bottled water over the 16-year period beginning in 1980. Include the units. Okay, so several things we need to kind of decipher from here. We are going all the way from 0 to 16. Okay, we need 4 subintervals, so I'm going to go ahead and erase this.
That means we need 4 trapezoids.
Lots of trapezoids. Alright, so I'm just going to guess that, well, we did 4 rectangles for our left Riemann sum. That only got us out to 8, so hopefully I just skip one of these every time.
Oh, look at that. Perfect.
And it works out. Okay, if it doesn't work out, then you've got issues. You're probably doing something wrong. Okay, double check to make sure it is from 0 to 16, or okay, it might give you a different value to go to. Okay, next thing I'm looking at, so trapezoidal method. Let's just start with that. Okay, we understand we're going to have to make some kind of trapezoid with this information. So remember the area of a trapezoid is going to be 1/2 base 1 plus base 2 times our height. Okay, so I'm going to just say 1/2. Okay, so remember these trapezoids are like turned sideways. if you were looking at it. So the height of our trapezoid is really going to be kind of the difference in our times. So this is going to be a difference of 5. The bases of those sideways trapezoids are going to be the heights of W. So it's going to be 4 plus 7.2. Okay, that was one trapezoid. We have 3 more to go.
Woo!
So we know it's going to be 1/2 again. Okay, the height of the trapezoid is going to be the difference of our bases. Here, that is going to be 3 from 5 to 8. Okay, the heights are going to be our W's, so 7.2 plus 14.5. Okay, then we're going to get 1/2 again. The difference is in our times, which is going to be 8 to 12, which is a difference of 4. Okay, our bases are going to be 14.5 and 22. And our last one here is going to be 1/2. The differences is going to be 4. And we're going to get 22 plus 32.
You
Okay,
can't.
now we're not done with this problem. That was just our trapezoid approximation.
And you can't do the shortcut because you don't have equal intervals between your differences for x. So I went ahead, you guys, because we already had some decimals going on, and did the 1/2 part as just 0.5. So there's the first trapezoid, 0.5, times that piece, which is the 5, and then in the parentheses, the sum of the bases, and then the next one, the 1/2, times the 3, the sum of the bases, plus the last one, or the third one, and then the fourth one. So all the way, kind of big long line horizontally across. And at least for that part, so we know what that part's answer is, we got 241.55. If you want to write
Nice.
down that answer.
241.55.
241.55.
Well, it's not our answer, okay? I just saw that there was a trapezoid. There's a lot of words there. I just saw trapezoid, so I knew I was going to have to do trapezoid for subintervals. All right, that part's done. But using the data in the table and the trapezoidal method with 4 subintervals, approximate the average rate for consumption. Okay, so W is the rate of consumption. If we want to find the average rate of consumption from 0 to 16, that's really going to be fave now. Okay, it's not asking for the average rate of change, it's average rate of consumption. So what we really want to do is 1/16 integral from 0 to 16 of W of T dt. Okay, which is pretty much going to equal this. The only difference is we just didn't have our 1/16. So we'll put big brackets and a 1/16 out front here. That does not look very straight. What happened there?
I don't know. So take that previous answer, multiply by 1/16, and you should get 15.097 approximately.
15.097. All right.
Include
Of course, we
units.
need to include our units. At least we don't need to interpret our answer this time, but we do include our units. Guys, they're asking for the average rate of consumption. Well, the rate of consumption is millions of gallons per year. Okay, and we'll talk a little bit more about that. But this is just going to be millions of gallons per year. Another way to think about it, we really integrated W of T dt, so we integrated millions of gallons per year, and when we integrate that, it's just going to be million gallons. Okay, but we had 1/time out front, which was 1/years, so when we do 1/years times millions of gallons, what you're going to end up is millions of gallons per year, which makes a lot of sense if we're asked to find the average rate of consumption. That would be a rate of consumption. Sweet.
We're on the back.
Yeah. How did I get 2 of these big problems?
No, I helped you. Every time.
Uh-huh.
I'm Vienna right now. I'm running the calculator.
Alright, so number 5, we got Frank proposes that the equation f of t equals 4.5 times 1.14 to the t models the data fairly well. Find the value of f prime of 10 and explain the meaning in the context of the problem. Okay, so probably in y1, we're going to say f of t equals 4.5 times 1.14 to the t.
And since that's a model that's modeling the same stuff as what we were talking about before, it's just a rule instead of a table, it's still about the rate of consumption of bottled water in millions of gallons per year. It's just a rule instead of the table giving us the information.
Yeah, it's representing the same exact thing. Like I said, this guy Frank
There's this guy,
just made up an equation that these numbers match pretty good. Maybe he like went in and did stats, a linear, what is it, exponential regression? Maybe he did exponential regression with that, and that's what he came up with. I don't know. But anyways, if we want to find f prime of 10,
Yep,
don't we just math 8 that?
you sure do, Mr. Herney.
Like, yeah, I don't want to find this derivative.
And we're going to evaluate it at 10. And we should get 2.186.
Okay, so f of t is really representing essentially the same thing as w of t. It's just an equation versus a table. Okay, so f of t is really in millions of gallons. Why am I rewriting this? I'll draw an arrow. There you go. Okay, it's still going to be millions of gallons per year. So the derivative of that is going to be millions of gallons per year squared. I'm assuming that they asked us to interpret instead of just our units, of course. Yep, we need to explain the meaning in the context of this problem. So what we're going to be doing here is we would say the rates of consumption of bottled water
In Oregon.
in Oregon. Okay, that was just describing what we're talking about. Now we can actually get into the meaning. So f prime of 10 is positive, so we're going to say is increasing at a rate of about 2.186 million gallons per year squared. Now, once again, it's not always going to be increasing at that rate, just at that instant. So at, or at the beginning of, we're talking 10, so it's going to be 1990 again. At the beginning of 1990.
Cool.
There are so many words. Write the equation of the tangent line to f of t at t equals 10, then use it to approximate f of 11.
Nice.
Sweet. I can squeeze this on here. So 6. So we want to approximate the equation of a tangent line. Write the equation of a tangent line. So we need a point and a slope is what I'm trying to say here. Okay, so we're talking about our equation f at 10. So our point is just going to be f of 10.
Remember where we stored f? It was in y1, so when you do y1 of 10, you get approximately 16.682.
And then we need our slope, which is going to be f prime of 10, which I believe we found in part 5.
On the previous line, 2.186.
Sweet. So we got our point, we got our slope. We can write the equation of our line at this time. So our equation is going to be y minus our points, so 16.682, equals our slope, 2.186, times x minus our x value, which is going to be 10. Okay, now we're going to have to approximate f at 11 using this equation. Okay, normally I would just leave it like this, but if I do need to, I guess, find what f of 11 is, I'm just going to add 16 over. I'm not going to distribute this, I'm just going to add 16 over. So my equation is really going to look more like y equals 2.186 times x minus 10 plus 16.682. Now if I want to approximate f of 11, remember this is not the value of f of 11, we're approximating f of 11. So f of 11 should be about 2.186 times 11 minus 10, which is just going to make 1 there, plus 16.682.
So just to not introduce any rounding error, I pulled down that 2.18 blah 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 with all the digits. Since it was just being multiplied by 1, you don't need anything, and I added the previous answer of the 16 point blah blah blah, no rounding error, and we got approximately 18.868.
18.868?
Yep.
Yeah. Is that it for number 6?
Yeah, but let's not.
Okay, let's
erase
talk
that.
about our units on that, even though we don't need them. Guys, f of 11, we just found the value at 11. Well, we approximated it. F was in millions of gallons per year, so this is Oregon consumed about 18.868 millions of gallons of water in the year 1991. Okay, we don't have an actual value for that from our table, although we could actually use our equation to find f of 11, but we approximated it.
Okay, so talking about number 7, and it has something to do with number 6, which is why we kind of like left that one up on the board. So I'm going to kind of try and squash it in up here. Number 7 says to find f of 11, because we actually have the rule of f, and remember f is in millions of gallons per year, it's a rate, even though it doesn't have a little tick mark, and then find the error in using the tangent line approximation in the previous problem. What can you conclude about f double prime of 11? So it's kind of like a very multi-step problem, and you really have to understand what's going on calculus-wise to be able to explain what you can conclude about f double prime of 11. So the first thing I need to do is just find f of 11, and we have a rule that's stored in y1, that is the f of t rule, then aren't we just really doing y1 of 11? So alpha trace y1 of 11, and so we would get 19.018 millions of gallons per year for the rate of consumed bottled water using this rule instead of the table. And it would be 11 years past 1980, so 1991, at the instant when the year's 1991. Okay? So we did that part, so that part's okay. And then it says, then find the error in using the tangent line approximation in the previous problem. So don't overthink that. All that's saying is, hey, find the difference between what your approximate answer was when you use the tangent line and what the actual value is for f of 11. Oh, so I just kind of want to find the difference between 19.018 minus the 18.868 that I just got from my tangent line approximation. And again, to not introduce any rounding error, I mean, there's my 19 point something. I'm going to do minus, so it takes that answer. Go up, scroll down, drag down the 18 point something, and get my error approximation. So there's a 6 behind a 4.9, so wouldn't that round up to 0.150? So that's my error change, right? As long as we're close to the point we're trying to approximate and we use a tangent line, it's going to be a pretty good approximation. You got to be close. It's called local linearization. All right, so we have that part done. Okay, so we're checking off as we go. What can you conclude about f double prime of 11? So this is where it kind of messes with your head, but I think if you draw a picture, you can kind of get there. So let's think about this. So the actual value of f of 11 in millions of gallons per year was 19.081. And the approximation that we got was 18.868 from our tangent line. So our actual value was bigger than our approximate value. So if I think about a picture, when we did local linearization, didn't we say it's all based on the concavity of the original function? So if the tangent line gives us something smaller than the actual value, then the tangent line has to be below the curve. And the only way that the tangent line is going to be below the original curve is if the original curve is concave up, right? The tangent line's below, so the tangent line is an under approximation or an underestimate of what actually is happening. What actual value was for f of 11 is bigger than the tangent line approximation. So we know that our tangent line's below the curve, so that must mean f double prime of 11 must have had to have been positive. If we are concave up, wouldn't this have had to have been a positive second derivative? So in that interval where 11 is, the original curve would have been concave up, right? So then we kind of just have to like conclude maybe it out in words. So on my conclusion, what I wrote down is that f double prime of 11 is greater than 0 because the original curve must have been concave up if the tangent line approximation is an underestimate of the actual value of f of 11. So at least in that interval, we must have had something that was concave up. So the tangent line would be below. Okay, so there's number 7. So we have 3 left. Definitely we're going to need more space now, so I'm going to do some erasing, and then Hernie can come start talking about the next part.
What? You don't want to take it from here?
Oh, did you get comfortable and now you want me to finish?
Oh, nap time.
Not music time, Mr. Hernie. Focus. Number 8.
Alright, number 8. Using Frank's equation, determine the average rate of change, AROC, in the rate of consumption of bottled water for the 10-year period beginning in the year 1980. Sweet. AROC. Oh,
I did leave your equation for Frank.
Oh, how nice of you.
Mm-hmm.
So if we want AROC, we're really going to do f of 10 minus f of 0 divided by 10 minus 0. Make sure you have that difference quotient.
And since our rule is in Y1, and this is calculator active, can't we just show Y1 of 10 minus Y1 of 0 all over 10 minus 0?
What does that come out to?
1.218.
Yay! Okay, I know it doesn't ask for it, but once again, guys, think about your units. F is in millions of gallons per year. We're dividing by time, so this is going to be millions of gallons. Per year squared. All right. Number 9, using Frank's equation, determine the average rate of consumption. Okay, it sounds like the same thing we just did. Okay, we found average rate of change. Now we want the average rate of consumption. Well, F is a rate of consumption. If we want the average rate of consumption, wouldn't we really be doing fave? So, what's our interval here? 16-year period now. So we're going to go 1 over 16. We're going to integrate from 0 to 16 of f of t dt.
And remember, our f of t rule is in Y1, so it's just a 1 over 16 minus 0 in front times math 9 from 0 to 16. And you should get approximately 15.320, tricky rounding. It's 199, so it'd be 320. And you have to have that trailing 0 to be correct to 3 places.
Man, these are a lot easier than our first ones.
we
Once
have a
again,
rule.
guys, we don't need to. It doesn't ask us for the units, but I want to think about the units again. The average rate of consumption is just going to be really millions of gallons per year.
Yeah, remember with fave, whatever the units are on what you're running fave on, those are gonna still be the same units. So we're boom, boom, down to number 10.
Heck yeah! Let's do number 10.
Oh,
MVT.
it's one of our favorite theorems, Mr. Herney.
It's my this is my favorite theorem. I like MVT. Find the time guaranteed by the mean value theorem for f of t on the closed interval 0 to 16. All right, so this one's a little bit different than normal. Normally they're asking you to kind of basically prove that it exists or
Right.
find what the slope is going to be, essentially. So it's an MVT problem, so let's do our hypothesis statement. F of t here is exponential. Okay, exponential, really this graph, if I were to graph it, probably looks something like this. Okay, exponential functions are continuous everywhere, they're differentiable everywhere. We just need to say that. F of t is exponential. Therefore, continuous and differentiable everywhere. Therefore, continuous and differentiable. Okay, I always like to just include these in the same on 0 to 16. I know Ryan likes to say it's continuous on 0 to 16 and differentiable on the open interval 0 to 16, which is technically the definition, but if this is true, then the other one's going to be true. And MVT holds true. Okay, so now we're asking, at what time does MVT hold true? So what we really need to do is show that A rock equals I rock. Maybe you want to write that. A rock equals I rock. So A rock, if we're really talking on the interval 0 to 16, I'm just going to erase these real quick. So we're really looking A rock equals I rock. So A rock is really going to be F of 16 minus F of 0 divided by 16 minus 0.
So you get 2.007, and maybe we don't want to round to three places because we have more to do, so let's keep all the digits. So 2.007 351364.
Did I get that right?
Yep, you got it.
Sweet. This equals I rock. Well, I rock is really the derivative of F. So, hopefully you guys remember how to take this derivative. I'm going to show you how to do this algebraically.
Which is nasty, and then I'll show you how to cheat and do it on your calculator.
Yeah, you guys are going to want to do it on your calculator, but hopefully some of you maybe did this algebraically. May hopefully have that skill. So, if I'm going to take this derivative, 4.5 is just a coefficient, so I'm going to leave that dude out front here, 4.5. The derivative of something to a variable, okay, is going to be that something to the variable. So we still have 1.14 to the t times the natural log of the absolute value of our base, which is going to be 1.14. Now that is obviously a positive number, so I'm just not going to do the absolute values, just make it parentheses.
Do you guys remember that from your time test? It's like a to the u or b to the u, a number based to a variable exponent. Holy cow, that's gross.
I don't want to rewrite this. So, guys, we're going to roll with this. Okay, so I want to solve for t. This is really 4.5 times natural log of 1.14. times 1.14 to the t. So I'm going to divide by 4.5 and natural log of 1.14. So I'm just going to abbreviate this nasty thing. Hey, 2.007. That's a fun year too. Divided by 4.5 times natural log of 1.14 is really going to equal 1.14 to the t.
So when I did that, I just said, take my previous answer and divide it by, but I had to do grouping symbols because I want to make sure it got like the coefficient in front and the natural log. Remember, natural log's a function, so it defaults a left parenthesis, so you have to close it to close the 1.14 that you're taking the natural log of, and then close it again to close around your whole denominator. And so that gives you 3.404 and a bunch of other digits.
All right, there's two different methods to solve this. We could ln both sides, which just means take natural log both sides, or we could log base 1.14. I'm going to just log base 1.14. Okay, really this t is going to come out front then. These cancel, and we're going to get t equals all of that.
So either take the natural log of that whole thing without introducing rounding error, or like Mr. Herney showed, the log little base, you can do that by alpha window option 5 of 1.14 of that whole great big number, so we're not introducing any rounding error, and you should get a time of approximately 9.350.
Nice. I'm just going to quickly show you, if you had done natural log, okay, you're still going to bring your t out front, but now we're going to have to divide by the natural log of 1.14. So I don't know if you guys see that, but this would be t equals, I have the natural log of all this nasty garbage. Divided by now the natural log of 1.14, which will give you the same answer.
Whew. Okay, so that's a lot of heavy-duty algebra and kind of a harder derivative that we didn't emphasize very much, and it's not really tested very hard either on the exam. So the cheat way to do it is if we went back to this step where we were thinking about AROC equals IROC, and we got our AROC answer already, which I think that part you guys can follow just fine, 2.07351.364. We just don't want to round that because we don't want to introduce any rounding error. And if we're trying to find the time where AROC equals IROC, IROC would just be the derivative of f, so f prime of t, right? Kind of just writing it as like, okay, this is the derivative in general, and I'm trying to find the time, what time t gives me the derivative answer of 2.007 on the f rule. So the thing that we're going to do is remember that we already have this f rule in y1, but I don't want to graph y1, I want to graph the derivative. So I want to really graph the derivative with respect to x of the rule that's in y1 evaluated when x equals x. If I do that on one of my y equals screens, it's going to graph the derivative. And I want to put this constant as well in one of my y equals screens. So I think what I did is I put this constant in y2, and then I was going to store this in y3 and turn y1 off, which we've done like a little bit of like turn some off and leave some on some other accumulation problems that we've done in the last couple of weeks. So there's like the f of t rule that Frank made. I'm going to turn him off. In y2, I'm going to put my AROC answer, so I'm going to type my constant, 2.007351364, which is just going to give me a horizontal line a tiny, tiny little bit above 2. So there's that. And in y3, I'm going to do math 8, and this will graph the derivative in general with respect to x of the rule. My rule is stored in y1 that I want to graph the derivative of, and it's not evaluating at a certain number. I want the slope everywhere, a little bit on every single little tangent line spot. So I go with respect to x. It's like x with respect to x. And one thing you might want to do is kind of shorten up your window. So since we were finding the times between 0 and 16, I went 0 to 16 by 1s. And I want to see where these two graphs intersect. And I mean, the idea is like if the value is 2.007, I just kept y min at -5, y max at +5, and went by 1s because I want to see where my curve crosses at 2 point something. So I mean, probably don't need a huge window. Or you can zoom fit it. So there's my horizontal line. Here's the curve. Remember, the derivative of e to the x is e to the x, and that's not exactly what we have, but we have like a growth curve. So the derivative kind of looks like the original curve. Oh, and it looks like they're only intersecting one time. Oh, I'm venturing to guess when I hit second trace to go into the calculate option and choose option 5 and do first curve and do second curve and hit guess, that I'm going to get that same value as what Mr. Herney got when he did all of that nasty algebra by hand. So the x is really the time, and look at that. We get 9.3497, which would round up to approximately 9.350. So that's the time that satisfies the mean value theorem, or MVT. Last minute thoughts? Are we good? We're good. Have a good weekend.